Hello everyone. I am Nikshita, MSc Chemistry student, and it is an audio recorded lecture for visually impaired student. Inorganic Chemistry, Unit 1, Metal-Ligand Bonding, Crystal Field Theory. Bethen and Van Vliet proposed the crystal field theory. This theory was originally applied to ionic crystals and therefore called crystal field theory. This theory is based on the following assumptions. Ionic ligands such as Cl negative, OH negative, Cn negative are regarded as negative point charge, and the neutral ligands such as H2O, NH3, Py are regarded as point dipole. Because these ligands are dipolar, if the ligand is neutral molecule like H2O, NH3, the negative end of the dipole is directed towards the metal ion. Metal ligand bond is not covalent, therefore there is no overlapping of orbitals, and the bonding in complex is purely electrostatic in nature. In complexes, two types of electrostatic forces. One is the attraction between the metal cation and the negatively charged ligand, or the negative end of the polar ligand. The second type of electrostatic interaction is the electrostatic repulsion between the lone pair of electrons on the ligand and the electron in the d orbitals of a metal cation, and the repulsion between the nuclei of metal cation and the ligand. The 5d orbitals in a free metal ion are degenerate. When a complex is formed, the electrostatic field of the ligand destroys and the degeneracy of these d orbital, that is, these orbital now have different energies. Shape of d orbital. In fact, there are a 6d orbital, each of them have 4 lobes. These orbitals are dxy, dyz, dzx, dx square minus y square, dz square minus x square, dz square minus y square. The three orbitals dx square, dyz and dzx lie in between the axes, and the three orbital dx square minus y square, dz square minus x square, and dz square minus y square lie on axes. In so far, there are only 5 independent d orbitals. One of them is regarded as the linear combination of dz square minus x square and dz square minus y square orbital because of the fact that these two orbitals have no independent existence. The orbital dz square minus x square has the probability of finding electron along the z and the x-axis, whereas the orbitals dz square minus y square has the probability of finding electron along the z and the y-axis. When these orbitals are combined, the resulting dz square minus x square minus y square orbital have probability of finding electron along z-axis twice that of along the x and y axis. The dz square orbital also have some fraction of probability along the x and y axis. This xy component has a ring shape, so therefore the 5d orbital are dxy, dyz, dzx, dx square minus y square, and dz square. The three orbitals dxy, dyz, and dzx lie in between the axes. The dx square minus y square orbital on x and y axis, and the dz square orbital on z axis, and the shape of dz square is different from the other four. All the 5d orbitals are Great, because the opposite lobes have the inconversion center with respect to the phase of wave function. The plus and the minus sign indicates the different phase of the lobes of a orbital crystal field splitting in octahedral complexes. In a metal cation, all the 5d orbitals are degenerate. In octahedral complexes, say MLX6 N positive, the metal cation is present at the center of octahedron and the six ligands are at the six corners. When six ligands are at infinite distance from the metal cation, the 5d orbitals of the metal cation will not be affected by the ligand electrostatic field and will remain degenerate. When the ligand moves towards the metal cation, there are two electrostatic forces. One is the attraction between the metal cation and the ligand. Second is the electrostatic repulsion between the d electron of metal cation and the lone pair of electrons of a ligand. Greater the force of attraction between the metal cation and the ligand, ligands are more closer to the metal cation. Hence, more will be the repulsion between the metal d orbital electrons and the lone pair of electrons. When the ligands are closer to the metal cation, an electrostatic repulsion also exists among the ligand, and the two repulsion cause to adopt the octahedral geometry that locates the ligand at the internuclear distance from the metal cation and as far apart from one another as possible. The force of repulsion between metal d electrons and the ligand electrons cause to increase in potential energy of a metal d electrons. Greater the force of repulsion, higher will be the potential energy. If all the six ligands approaching the metal cation surrounded it spherically symmetric, that is, all the ligands are at equal distance from each of the d orbital, the energy of each of the first 5d orbital will rise by the same amount and all the 5d orbitals will still remain degenerate. And this is an hypothetical situation and hence the average energy of a set of d orbital. In a actual octahedral complexes, spherical symmetrical field is never obtained. Therefore, all the 5d orbitals are not affected to same extent. Since the two orbitals point directly towards the ligand and three orbitals point in between the path of approaching ligand. Therefore, the dx minus y square and dz square orbital will be more strongly repelled than that dxy, dyz and dzx orbital. Therefore, the energy of the dx square minus y square and dz square will be raised and that of other three orbitals which lie far away from the ligand will be decreased relative hypothetical energy state. The 5d orbitals which were degenerate in free metal cation are now split into two sets of orbital of different energy. A higher energy level with two orbitals dx square minus y square and dz square having the same energy and a lower level with the three equal energy orbital dxy, dyz and dzx. The set of dx square minus y square and dz square orbitals are referred to as EG set and which has doubly degenerate and the set of dxy, dyz and dzx orbital is referred to a T2G set which is triply degenerate. Firstly, the degenerate d orbital in 5 in free ion, and then the average energy, and then splitting takes place, and the crystal field splitting in octahedral field is T2G having orbitals dxy, dyz and dzx, and Eg having orbitals dx square minus y square and dz square, and the energy gap is 10 dq. The distance between the metal cation and the ligand has remained the same, and the net potential energy of the system must remain the same as that of the spherical field before splitting. This state of average energy is called the barycenter, and the energy of barycenter remain constant, and the total energy decreases of T2G set must be equal to the total energy increase of Eg set, and there are two Eg orbital, and there must be increased by a zero point 0.6 delta knot, and 3 T2G orbital must decrease by the zero point 0.4 delta knot per electron, and the decrease in the energy of T2G orbital stabilize the complex by zero point 0.4 delta knot, and the increase in the energy of Eg orbital destabilize the complex by zero point 0.6 delta knot. Distribution of d electron in octahedral complexes. The distribution of d electron in T2G and Eg orbital depends upon the magnitude of delta knot. When the magnitude of delta knot is smaller, then it is assumed that all the 5 d orbitals are degenerate, and the distribution of d electrons in T2G and Eg set takes place according to the Hund's rule of maximum multiplicity. T2G first, second, and third, and then in Eg fourth and fifth, and then is T2G sixth, seventh, and eighth, and then in Eg ninth and tenth. In these complexes, no pairing of electron will take place, and the arrangement of d electrons remains same as in the free metal. The complexes in which the magnitude of a delta knot is larger, the energies of T2G and Eg orbital differ significantly, and the distribution of d electron does not obey Hund's rule of maximum multiplicity. Then the T2G is first electron, second, third, fourth, and fifth and sixth electrons, and then fill the Eg orbital 7th, 8th, ninth, and 10th electron. In these complexes, the pairing of electron takes place in T2G orbital from D4, D5, D6, and D7 configuration. The value of delta knot is smaller or larger these. There is no difference in the d electron configuration for D1, D2, D3, D8, D9, D10 system. Weak field or ligand high spin complexes. In weak field octahedral complexes of 3D series transition metal with oxidation state greater than or equal to plus 3, the value of delta knot is smaller, and there will be no pairing of d electrons. The complexes having maximum number of unpaired electrons are called a high spin or a spin free complexes. The term high spin or a spin free is used because these complexes have same number of spin as in d orbital of free metal cation. Strong field or low spin or a spin paired complexes. In strong field octahedral complexes of 3D series transition metal with oxidation state in journal greater than smaller than or equal to plus 2, the value of delta knot is large, and these complexes have maximum number of paired electrons are called a low spin or a spin paired complexes. Pairing energy. The energy required to force the two unpaired electrons in one orbital is called a pairing energy. If the delta knot energy is greater than the pairing energy, it favors the low spin complexes. If delta knot energy is less than the pairing energy, it favors the high spin complexes. If delta knot energy is equal to the pairing energy, high spin and low spin complex equally exist. Crystal field stabilizing energy in octahedral complexes. In an octahedral complexes, the d of the metal cation are split into the two sets of different energy, 2 to T2G of lower energy and EG of higher energy, and the energy gap between this is 10 dq. The complex ion with one electron in one of the T2G orbital has an energy of minus zero point 0.4 delta naught and related to the barycenter. This indicates that in a complex of D1 configuration, zero point 0.4 delta naught energy is released, and this released energy is called a crystal field stabilizing energy in the complex ion. For D1 complex, the electronic configuration is T, T2G1 and EG0. CFSE is equal to minus zero point 0.4 multiply 1 is equal to minus zero point 0.4 delta naught. For D2 complex, the electronic configuration is T2G2 and EG0. The CFSC is equal to minus zero point 0.4 into 1, then is equal to minus zero point 0.8 delta naught. For D3 complex, the electronic configuration is T2G3 and EZ0 and is equal the CFSC is equal to minus zero point 0.4 into 3 delta naught is equal to minus 1.2 delta naught. For D4 complex for high spin, the electronic configuration is T2G3 and EG1 is equal the CFSC is equal to minus zero point 0.4 into 3 plus zero point 0.6 into 1, that is equal to zero point 0.6 delta naught. For D4 for low spin, the electronic configuration is T2G4 and EG0. The crystal field stabilizing energy is equal to minus zero point 0.4 into 4 plus zero point 0.6 into 0, then plus pairing energy. So is equal to 1.6 delta naught plus pairing energy. For D5 system, high spin, the electronic configuration is T2G3 EG2 and the CFSC is equal to minus zero point 0.4 into 3 plus zero point 0.6 into 2, so is equal to 0 delta naught. And for low spin, the electronic configuration is T2G5 and EG0. CFSC is equal to minus zero point 0.4 multiply 5, that is equal to minus 2.0 delta naught plus 2 pairing energy. For D6 system, high spin, electronic configuration is equal to T2G4 and EG2. The CFSC is equal to minus zero point 0.4 into 4 plus zero point 0.6 into 2 is equal to minus zero point 0.4 delta naught. For low spin, the electronic configuration is equal to T2G6 and EG0. The CFSC is equal to minus zero point 0.4 multiply 6 plus 2 pairing energy. So is equal to minus 2.4 delta naught plus 2 pairing energy. For D7 system high spin, electronic configuration is equal to T2G5 and EG2. The CFSC is equal to minus zero point 0.4 multiply 5 plus zero point 0.6 multiply 2 is equal to minus zero point 0.8 delta naught. And for low spin, the electronic configuration is equal to T2G6 and EG1. The CFSC is equal to minus zero point 0.4 multiply 6 plus 0. So is equal to minus 1.8 delta naught plus pairing energy. For D8 system, the electronic configuration is equal to T2G6 and EG2. The CFSC is equal to minus zero point 0.4 multiply 6 plus zero point 0.6 into 2. So is equal to minus 1.2 delta naught. For D9 system, T2G6 and EG3, the CFSC is equal to minus zero point 0.6 delta naught. For D10 system, The electronic configuration is T2G6 and Eg4. The crystal field stabilizing energy is equal to 0. For a DN system, high spin complexes with electronic configuration T2G की power P and EGQ, though CFSC is equal to minus 0.4 P plus 0.6 Q delta naught. For a DN low spin octahedral complexes with electronic configuration T2G, P and EGQ, the CFSC is equal to minus 0.4 P plus 0.6 Q delta naught plus M pairing energy. Crystal field splitting in tetrahedral complexes. A regular tetrahedral geometry is obtained when a metal cation or an atom is placed at the center of a cube and the four ligands occupy the alternate corners of a cube. The dxy, dyz and dzx orbitals of a metal cation experience more repulsion from the ligands and are of high energy. Those of the dx square minus y square and dz square orbital to maintain the rule of the center of gravity. The dx y, dyz and dzx orbital are the 0.4 delta t above the barycenter and the dx square minus y square dz square orbital are 0.6 delta t below the barycenter. The G subscript is not used with the T2 and E set because the tetrahedral complexes have no inversion center and the difference in the energy of E and T2 set is represented by the delta T, where the T stands for the tetrahedral and the crystal field splitting is just reverse of the octahedral complexes. The crystal field splitting in tetrahedral complexes is smaller than that of octahedral complexes. It is observed that delta T is equal to 4 by 9 of delta naught because the number of ligands are two-thirds of the octahedral complexes and therefore the splitting of d orbital is also the two-thirds. None of the ligands point directly towards any of the 5d orbital. Therefore, the splitting is reduced by roughly two-thirds. Tetrahedral complexes are always high spin because delta T is equal to 4 by 9 of delta naught. That is, delta T is much smaller than the octahedral splitting delta naught. Second, delta T is always less than that of the pairing energy. Factors affecting the magnitude of delta. Oxidation state of metal cation. The higher the oxidation state of metal cation, the greater will be the magnitude of delta. Example, delta naught for the COH2O6 2 positive is equal to 929,200 centimeter inverse and delta naught for the COH2O6 the oxidation state 3 positive 20760 centimeter inverse. Second, same oxidation state of metal cation but the number of d orbital is different. The magnitude of delta naught decreases with the increase in the number of d electron. It is due to the fact that the higher number of d electron prevent the ligand to come closer the metal cation. Principal quantum number of a d orbital of a metal cation. In case of complexes having the metal cation with the same oxidation state and the same number of d electron, the magnitude of delta or the analogous complexes within a given group increases above 30% to the 50% from the 3D to the 4D and by above the same amount for the 4D to the 5D because on moving to the 3D to the 4D and 4d to the 5d transition series, the size of d orbital increases and the electron density decreases in them, and the ligand can approach the metal cation with a large d orbital more closely. Therefore, there is a less steric hindrance round a large metal cation. Number of ligand. The magnitude of a delta increases with the increase of the number of ligand. For example, delta naught is greater as compared to delta T. Nature of ligand. The ligand are classified as weak and the strong ligand. The ligand which cause a small decrease of splitting of d orbitals are called weak ligand, and the ligand which cause a large splitting are called a strong ligand. The common ligand have been arranged in the order of their increasing crystal field splitting power to cause the splitting of d orbitals from a study of their effect on the spectra of the transition metal. I negative, Br negative, S2 negative, SCN negative, Cl negative, N3 negative, F negative, urea O negative, C2H5OH, C2O42 negative, O2 negative, H2O, NCS negative, GLY, EN, SO32 negative, NH2OH, BPY, FPHEN, NO2 negative, CH3 negative, C6H5 negative, R3P, Cn negative, and CO. This order is usually called a spectrochemical series, and the distribution of d orbital in tetrahedral complexes. E first, second, T2 third, fourth, and fifth electron. E is sixth and seventh electron. T2 8, 9, and 10 electron. For tetrahedral complexes, delta T naught is smaller than the pairing energy. Crystal field stabilizing energy in tetrahedral complexes. In tetrahedral complexes, the d orbitals of the metal cation are split into the two sets of different energy, E of lower energy and T2 of higher energy. The separation between the two sets is equal to the delta T. The E set has an energy of minus 0.6 delta T, and T2 set has an energy of plus 0.4 delta T relative to the barycenter. For a Dn tetrahedral complexes with E having p electron and T2 having q electron, Nick configuration. The CFSE is equal to minus 0.6 p plus 0.4 q delta T and minus 0.6 p plus 0.4 q multiply 4 by 9 of delta naught is equal to minus 2.7 p plus 0.18 q delta naught. Tetrahedral distortion or Jones-Taylor distortion. In general, the distortion that occur in octahedral complexes is the tetrahedral distortion. A tetragonal distortion occur when the two trans ligands on the z-axis in the octahedral complexes, say Ml6, are moved either towards the metal ion or away from the metal ion or atom. Motion of the trans ligand along the z-axis towards the metal cation produces a tetragonal compression, and the motion of these ligands away from the metal cation produces a tetragonal elongation. The shape of a regular octahedral and tetrahedral compression and the tetrahedral elongation complexes. The condition which causes such type of distortion was described by the Jones-Taylor distortion theorem, and this theorem states that any nonlinear molecule is an electronically degenerate state, is unstable, and the molecule becomes distorted in such a way that as the remove degeneracy and lower its symmetry and lower the energy. Electronical degenerate state refers to the situation in which an electron can be arranged in more than one orbital of a equivalent energy. This situation arises when the degenerate orbitals are unsymmetrically filled. Uh, First, d orbital in free ion. Average energy of orbital in a spherical crystal field. Then T2g dxy dyz and dzx orbital, and Eg having dx square minus y square and dz square having orbitals. Then splitting of d orbital in tetragonal elongation. Higher energy of dx square minus y square and lower energy of dz square, and then higher energy of orbital dx square by lower energy of dyz and dzx. In regular octahedral field, the Eg orbital are degenerate. However, if the Eg orbital are asymmetrically filled, that is either dx square minus y square or dz square orbital contains one electron more than that of other, then the Eg orbital are split. If the dz square orbital contain one electron more than the dx square minus y square orbital, then the ligand approaching along z axis will be repelled more than the ligands approaching along x and y axis. It is because of the fact that the electron density of dz square orbital is greater than that of the dx square minus y square orbital. Therefore, the ligands along the z axis are moved away from the metal cation relative to those on the x and y axes, which move towards the metal cation, and the reason for the distance between the metal cation and the ligand to be shorter and on x and y axis, and is that of the ligand repulsion is decreased as the ligand move away from the metal cation on z axis. Therefore, the distance between the metal cation and the ligand on z axis becomes larger, and the distance between the metal cation and the ligand on x and y axis becomes shorter, and thus the complex undergoes a tetragonal elongation. Since the ligand on z axis are at larger distance from the metal cation than that of the ligand on x and y axis, therefore the dz square orbital will experience a decrease in repulsion from the ligand, and therefore energy of a dz square orbital will decreases, and hence the dz square orbital is stabilized, and the dx square minus y square orbital will experience an increase in repulsion from the ligand, resulting in an increase in energy, and hence the dx square minus y square will therefore be destabilized with the barycenter and remaining constant. In similar way, the energies of the orbital having z square component will decrease as that of dx square will increase a part of the degeneracy in the T2g orbital is removed. Therefore, the overall result is that the Eg orbital split into the two levels as upper dx square minus y square and the lower dz square, and the T2g orbital is split into the two level as upper dxy and a lower degenerate dyz and dzx. The tetragonal elongation is generally called a tetragonal distortion and is observed in most of the tetragonal distorted complexes. If dz dx minus y square orbital contain one electron more than that of dz square orbital, then the ligand approaching along x and y axis will be repelled more than the ligand approaching along the z axis. It is because of the fact that the electron density in dx square minus y square orbital is greater than that of the dz square orbital. Therefore, the ligand along the x and y axes are moved away from the metal cation and relate to those of the dz axis and which move towards the metal cation. And the reason from the distance between the metal cation and the ligand to be shorter on the z axis is that the ligand repulsion is decreases as the ligand move away from the metal cation on x and y axes. Therefore, the distance between the metal cation and the ligand on x and y axis become larger and become shorter on z axis. Therefore, the complex undergo a tetragonal compression. Since the ligand on x and y axis are at longer distance from the metal cation than that of the ligand on z axis, therefore the dx square minus y square orbital will experience a decrease in repulsion from the ligand and therefore the energy of a dx square minus y square orbital will decreases. The dz square orbital will experience an increase in repulsion from the ligand resulting in an increase in energy with the barycenter remaining constant. In a similar way, the energies of a orbital having x and y component will decreases and that of having z component will increases. In tetragonal compression, four ligands on x and y axis repels the high density of electron in dx square minus y square orbitals, whereas in tetragonal elongation only two ligands on z axis repel the high density of the electron in dz square orbital. Therefore, there is more repulsion in tetragonal compression than that of tetragonal elongation. Therefore, the tetragonal elongation is more stable than that of tetragonal compression. Thus, the tetragonal elongation is known as a tetragonal distortion. Consequences of John Taylor distortion. Stability of Cu2 positive complexes. Ba2 positive Sr2 positive, Ca2 positive, Mg2 positive, Mn2 positive, Fe2 positive, CO2 positive, Ni2 positive, Cu2 positive, and greater than Zn2 positive. This series was called a Irium-William series, and the extra stability of a Cu2 positive is due to the John Taylor distortion. During this distortion, the two electrons are lowered in the energy, where one is raised as equal amount of energy. The complexes En thrice and 2 positive is unstable because the John Taylor distortion causes strain into the ethylene diamine molecule attached along Z axis. Trans CuEn2 H2O2 whole positive 2 positive is more stable than the cis because the John Taylor distortion causes strain in the ethylene diamine molecule along Z axis in cis form. In crystalline KCuF3, the 2CF distance on Z axis is less than that of the remaining CuF distance in XY plane. It is due to the John Taylor distortion. Complexes of Au2 ion are unstable and undergo disproportion to the Au1 and Au2, whereas the copper 2 and the Ag2 are comparatively more stable. The high value of delta causes a high destabilization of the last electron in the dx square minus y square orbital, and the Ag2 becomes the extremely reactive. The splitting of the absorption band in the electronic spectra of a complex is due to the John Taylor distortion. Applications of CFSC. Enthalpy of hydration of the transition metal ion. In an aqueous solution, the metal cation are surrounded by the polar water molecules, and the process is called hydration. The hydration energy of a metal cation increases with increase in effective nuclear charge and the decreases in ionic radii. Because these two factors bring the water molecule closer to the metal cation and increased electrostatic attraction between the metal cation and the water molecule. The hydration energy should be increased regularly from the Ca2 positive to the Zn2 positive, and the straight line should be obtained as shown. When a dipositive or a tripositive metal cation of 3D series transition series metal get hydrated, a high spin octahedral aqueous complex is formed. And not only the hydration energy but the CFSC is also involved. Experimental He is equal to the theoretical or expected He plus CFSC. Refers to the hydration energy. Lactic energy. Lactic's energy is the change in the energy when one mole of the an ion crystallized is formed from an constituent gaseous ions. The correct value of crystal lattice energy can be calculated by the substituting the CFSC from the experimental lattice energy. Ionic radii of a complexes of divalent metal ions of 3D series transition element in the low spin or a high spin octahedral field might be expected to decrease the regular from Ca2 positive to the Zn2 positive because the increasing effective nuclear charge and the poor shielding effect of d electrons causes the increase of force for of attraction between the metal cation and the ligand may approach the metal cation more closely, but some ions shows discriminations from the regular trends of the decreasing ionic radii. Structure of the spinel. Spines are the mixed metal oxide having the formula Ab2O4, where A can be grouped into 2 metal or the transition metal plus 2 oxidation state of B. B can be grouped into 13 metal or transition metal in plus 3 oxidation state. Oxide ion from the CCP or FCCP lattice with the 4 octahedral voids and the tetrahedral voids per Ab2O4. Number of tetrahedral voids is equal to 2 multiply number of octahedral voids. Number of octahedral voids is equal to number of lattice points. Number of tetrahedral voids is equal to 2 into number of lattice points. Spinels are classified into two categories: normal spinels and A2 positive ion occupy 1/8 of the tetrahedral voids and B3 positive ion occupy half of the octahedral voids. Inversion spines. In the inversion spinel, A2 positive ion occupy 1 by 4th of the octahedral void along with the half of B3 positive ion, whereas the other half of B3 positive ion occupy 1 by 8th of the transition metal vacancies. Prediction: the structure of the spinels. If the CFSE for the B3 negative ion in octahedral void is greater than that of the B3 positive of the tetrahedral void and the A2 positive in the both the tetrahedral and the octahedral void, the spinel will be the normal. If the CFSE of the A2 positive ion in the octahedral void is greater than that of the A2 positive in tetrahedral and the B3 positive in the both the tetrahedral and octahedral voids, then the spinel will be inverse. First Mn3O4 changes into Mn2O4 weak field ligand. In octahedral, Mn2 positive having electronic configuration T2G3 Eg2, the CFSC is 0 and the tetrahedral electronic configuration is E2 and T23, the CFSC is also 0. For Mn3 positive, the electronic configuration is T2G3 and Eg1. The CFSE is minus 0.6 delta node. And in tetrahedral, Mn3 positive is equal to E2 and T22 and CFSE is equal to minus 0.18 delta node. Then it is a normal spinel. Similarly, in case of Fe3O4, changes into Fe2O4. In octahedral complexes Fe3 positive, the electronic configuration is T2G3 and Eg2, the CFSC 0. In tetrahedral Fe3 positive having electronic configuration E2 and T23, the CFSC is also 0. In octahedral Fe2 positive, the T2G4 and Eg2, the CFSC is equal to minus 0.4 delta node. And for in tetrahedral Fe2 positive, the CFSC is 0 minus 0.27 delta note, the inverse spinel. Limitations of the crystal field theory. The CFT consider only the metal d orbital and the s and p orbital are ignored. And this theory has not considered the covalent character in transition metal complexes, and the CFT also has also not considered the pi bonding in the complexes. The CFT cannot explain the relative strength of the ligand as given in the spectrochemical series. The compounds like the CrCO6 and NiCO4, in which the metal is in zero oxidation state and the ligand is neutral, having no electrostatic attraction between the metal and the ligand. Ligand field theory. The covalent bonding in complexes has been explained by the ligand field theory. According to the ligand field theory, the covalent bond between the metal and the ligand are formed by the linear combination of the metal atom atomic orbital and a ligand group orbitals. The symmetry of the ligand group orbitals must match the symmetry of the metal atomic orbital, such that there is a positive overlapping of the ligand group orbital with the metal orbital along the bonding axis. Sigma bonding in octahedral complexes. In octahedral complexes, the ligands are approaching the metal cation on x and y and z axis. Therefore, the ligand group orbital will overlap with the metal orbital along the octahedral bonding axis to form a sigma bond, and the metal cation has in its valence shell 1 ns and 3 np and 5 n-1d orbital. The octahedral symmetry have transformed to s orbital into ag and p orbital into t1u, d orbital into t2g and eg set. Metal orbital or symmetry. S changes into A1G and Px, Py and Pz changes into T1U and dx y dyz and dzx into T2G and dx square minus y square dz square is changes into Eg. A1G orbitals is spherical in shape, therefore it can be overlapped with the ligand group orbital on all axes, and the T1U and Eg orbitals are pointing along the axis, therefore these orbitals can be formed the sigma bonding on octahedral axis by the overlapping with ligand group orbitals, and the T2G orbital lie between the axes, and these orbitals are not capable to overlap with the ligand group orbital to form the sigma bond. Therefore, out of the 9 metal orbital only 6 orbitals participate in the sigma bond formation. The T2G orbital are considered to be non-bonding molecular orbitals in octahedral complexes, whereas the no possibility of the pi bonding. If the ligand have orbitals of same symmetry as that of metal T2G orbital, then the T2G metal orbital will be involved in pi bonds. Each of the 6 equivalent ligand atom contributes an atomic orbital or hybrid atomic orbital to form a sigma bond. In an octahedral complexes, the 6 atomic or hybrid orbitals of 6 ligands are pointing along plus x plus y minus y plus z and minus z axes, which have been represented by the sigma x, sigma minus x, sigma y, sigma minus y, sigma z, sigma minus z. And the diagrammic representation shows the MO diagram. In the bonding molecular orbitals are e.g. T1U and A1G in, and the non-bonding molecular orbital are T2G, and anti-bonding orbital are e.g. star A1G star and T1U star.